Hello, students. I want to share with you one of my favorite uh, demonstrations and lessons of all of physics, and that is circular motion. So I hope you enjoy this video, and let me know if you have any suggestions. Thank you. By the laws of physics, Okay, so let's pause there. I basically have a cup on a platform without any glue, without anything on it except water in the cup. So you can see here, water, water in the cup and a platform and a whole bunch of strings tied on the platform. I should be able to move this around in a circle.
Oh!
So you're gonna tell me there's not even one drop of water?
Ooh, did it spill?
As some of you heard in the last part of the clip, water was spilled onto the sink, confirming that there was water in there, but not a single drop has spilled.
There you go.
Yeah, and it stays there,
Nice.
and then
Alright.
it's magic.
I don't
want to
I
get,
don't
yeah.
want to splash it.
Please sit down. If this was live, we would have. Okay, you.
Okay.
Okay.
Ooh.
Oh, you're still in.
Here, a student of mine wanted to explain and teach part of the lesson. I love when students get involved like that, so that's what I wanted to show you here.
I feel like the water will spill. Oh!
Here, of course, we're just having fun, a little over the top, but always a curious thing if when students ask, can you spin it sideways? So there you go. I hope you enjoyed the video. I hope that through this demonstration and video that you realize that physics is everywhere in the world, and that as you learn the lesson, as we're going to get started with the presentation, I want you to really think about numbers not as just numbers, but an application to real live world demonstrations and phenomena. So that's what I want you to think about, and let's get started on the lesson. Okay, hello everybody. So here is the presentation for circular motion. What we have here is, sort of like a planet and a moon circling around it. And this shows that circular motion exists even in our universe. Earth and moon, and even the Earth-Moon system revolving around the sun is also an example to this circular motion. So there's circular motion in the macro sense, where in the universe, gravity causes circular motion to occur. And also it is caused in the micro sense, where you can see it around us in the world and even in the microscopic level. Anyway, let's talk about uniform circular motion. Any object traveling in a circular motion has constant speed and is constantly changing velocity. So, which means it's changing in direction, but not in magnitude. So, again, changing velocity, which means that it is changing direction, as you can see here, going around in a circle, this object. It's not really changing how fast it's going around, but it's merely changing the direction. So here, going up, but going to the right as it goes around the circle. So, continuing, how do we define velocity? So velocity is defined, if it's constant, as a change in displacement here, and the change in time. So we're considering actually the change in displacement as it goes around over the change in time. What distance or displacement are we talking about? Well, in a circle, the amount of distance or displacement that you go around is the circumference. Well, circumference is defined to be 2 pi r, or pi times the diameter. So we can calculate that if they gave us the diameter or the radius of the circle. What t are we talking about? Well, the time for one revolution around the circle is called the period. So the time, the change in time or time elapsed, is going to be the time it goes around once around in a circle. So velocity also at that singular moment is tangent or tangential to the circle at all points. So let's take a look. And also this equation here gives us the more expanded form of the displacement divided by the amount of time it goes around in a circle. So velocity equals 2 pi r, which is the circumference of the circle, which is the distance around the circle, divided by the time elapsed going around it once. So let me show you what we mean by tangential to the circle at all points, or tangent to the circle. So at each point, you can see that it only touches the circle once and has a certain direction that has a singular point on the circle. So, and that's what tangent line means. It only, intersects one point around the circle. So, as you can see here, each arrow is 90 degrees to the line to the center, and you can see all around the direction changes. So let me ask you a question. If this is true, why does anything move around in a circle? How does it move around in a circle? What causes it to move around in a circle? And the answer is the centripetal force. So we're going to learn about this force right here. Inertia causes the object to travel straight. So we learn about what inertia is, right? Any object that moves will continue moving unless acted on by an external force. And also whatever is at rest will stay at rest. So that's the law of inertia, and it causes the object to continue traveling straight. A centripetal force will bend the path. So paths can be bent by forces, which causes a sort of an acceleration, which causes a different direction in the line of motion of an object. The centripetal force bends the object's path into a circle, pulling towards the center. That's what centripetal force is. It's a center-seeking force, which allows the object to be pulled towards the center, which allows the circular motion to happen. One of the things that I always like to connect this lesson about is the machine Gravitron. If you ever been on one, if you ever been on one of those things in in one of those fairs, there's a Gravitron which spins you around, and you sort of feel like you get stuck to the wall. You feel like you're pushed against the outside of the edge of the ride and pinned there. You feel like you're experiencing some sort of centrifugal force throwing you towards the outside of the ride. But in the laws of physics, it's not really pushing you out. The wall is pushing you in. So let's take a look. What is really happening here? Well, as the Gravitron starts to spin, friction between your body and the ride allows you to move, and also the wall will push you towards the center. So the friction between you will allow the velocity to happen, and you're really going tangentially, you're being thrown tangentially, but the wall is keeping you inside towards the center. Once you're moving, your body wants to move straight, tangentially to the circle, but the forces will keep you in. And this is exactly what happens to the planets. This is exactly what happened in the demonstration that I showed you. And that's basically it. The wall keeps pushing you back in towards the center of the ride. So that's basically what we have here. What is that sensation that you feel? Centrifugal force is a fictitious inertial force that is experienced from the inside of the circular motion system. It's really what you feel. You feel like you're being drawn out, but really the centripetal force is a true force that pushes and pulls you. It pulls an object towards the center of the circular path. It's what actually happens. So that's the physics part behind it, where the wall is pushing you in, as opposed to what you feel, being pushed out. You're actually being thrown tangentially to the circle, but the force on the wall is pushing you inside, which changes your direction. So let's talk about centripetal acceleration. Centripetal force is a net force that causes an acceleration to happen. The acceleration is in the same direction as the net force, which is towards the center. So the equation for that is acceleration centripetal equals velocity squared divided by r. R is the radius. V is the velocity, how fast it's going. You have to square that, and that velocity squared divided by the radius will equal to the centripetal acceleration that you experience. So example number 1. What is the centripetal acceleration of a toy ball on the end of a 1.44 meter long string if it is moving at 12 meters per second? Now, sometimes students ask me, okay, we don't have enough information here. We have the velocity 12 meters per second, and we're looking for centripetal acceleration, but we do not have the radius. How are you supposed to figure out the radius from a 1.44 meter long string? Well, let's imagine if we were to spin around a 1.44 meter long string. Well, first of all, that's a very long string, but still, if we circle it around, that should be the radius itself. If you can imagine that, you can clearly see that if you have that much of a long string and you're spinning it around, the radius is just that amount. So you can take this as the radius and plug it into the equation as you see here. Acceleration centripetal equals v squared over r, and you're plugging in the velocity, you're plugging in the radius directly, and you get 100 meters per second squared. Centripetal force is also defined to be A equals F net over M, and we saw that equation way before in our lessons. That could be also transformed into F net equals mass times acceleration, which is more of the famous formula that Isaac Newton has come up with. If we combine that with the centripetal acceleration formula, we can get our final equation for force, which is going to be Fc equals mass times velocity squared divided by r. So we're taking these two equations, substituting them in, and getting the main equation that we have here. So let's take another example. What is the centripetal force acting on a 2,000 kilogram airplane if it turns with a radius of 1,000 meters while moving at 300 meters per second? Now, of course, I forgot to mention, if you want to pause the video and try it out for yourself, you're more than welcome to do that. But for the sake of the video, I want to continue on by identifying the givens and then plugging it into the equation and then solving it just like we do in any physics problem. So we have what we want to identify is the centripetal force. So that's what we want to calculate, and you have the formula right there from the notes. Acting on a 2,000 kilogram airplane. Now that describes the airplane, which describes the mass of the airplane, since it is the units of a kilogram. So you have to know that for our physics purposes here. 2,000 kilogram, you have to be able to label it as a mass, even though it doesn't specifically tell you that it is mass. If it turns with a radius r equals 1,000 meters, that's part of our givens, while moving at 300 meters per second, that must be velocity because of our units meters per second, and it is moving at that rate. So we have our equation, we plug it in, and we want to get acceleration first in this method. There are many methods into solving this. We could have solved it by plugging into the main centripetal force equation and do it in one step, but here we can do it in two steps by plugging into the centripetal acceleration formula, find the centripetal acceleration, and then I'm not sure if you could see this because of my screen. Maybe I can move it here. You can see clearly that you can plug it into F equals ma equation and solve it in two steps and plug in your relevant givens. Mass is 2,000 kilograms and acceleration is 90 meters per second squared, and you can solve for the force. Make sure you plug in the units and make sure you have the equations, relevant equations visible there on your paper. So example number 3. Is it possible for a 1,000 kilogram car to make a turn with a radius of 50 meters while moving at 15 meters per second with rubber tires on dry asphalt? So let's take a look at this example. Now it looks very complicated, but we can solve it one step at a time. So they're asking, is it possible for a 1,000 kilogram car to make a turn? So making a turn is actually a centripetal force equation problem, because in order to make a turn, you need to make a turn in a circular manner. So that automatically tells you, okay, I need to solve the centripetal force on this thing. They even gave us the radius. So that should give you a clue that it's a radius of a circle and that we need to plug it into that formula. And it's also moving at 15 meters per second. That's the velocity that perfectly fits the centripetal force formula. Now, they also give us another clue that it is on rubber tires on dry asphalt. And one of the things that we learned in the previous lessons is that rubber tires on dry asphalt gives us a coefficient of friction, which allows us to find the frictional force, which is what they're trying to connect here. So, as we can see, we automatically go to the centripetal force formula and we plug in our numbers, 1,000 kilogram car for the mass, 15 meters per second. Now that is to be squared here. This is not the units, but this 15 has to be squared to 25, multiplied by 1,000, divided by 50 meters of the radius, which gives us 4,500 newtons. So that's actually, if we were to analyze the situation, this is the minimum amount of force that we need in the friction in order to make this turn. So the question is, do we have enough friction force in order to make the turn? If it is more than 4,500 newtons, then we have enough frictional force to make the turn. If we do not exceed 4,500, if it's lower than 4,500 newtons, then that means it's going to slip. It's going to slip and it's going to slide. Just like if there was snow or ice on the floor, it's definitely going to be less than the centripetal force. The frictional force is going to be definitely less than 4,500. But if there is rubber on dry asphalt, we will see it definitely should have more than 4,500. Let's take a look. So I know that the centripetal force has 4,500 newtons. That's the minimum force that we need to make the turn. We have the frictional force, which is the coefficient of friction. This Greek letter mu represents the coefficient of friction, which is the strength of the surfaces that are in contact. And we have the normal force, which is the same as the force of gravity, which is the weight. So for the sake of this, purposes of this video, I've already calculated the normal force for you, which is just the force of weight on this 1,000 kilogram car. So I plugged it in here. And I also searched up in the reference table the coefficient of friction between rubber tires and dry asphalt, which happens to be 0.85, which I used the static because the tires are rolling onto it. If it's sliding, you would use the kinetic coefficient of friction, but here I use the static because the tires are rolling onto the surface, which means the object is not sliding on the surface. So we plug in the numbers and we solve, and we have the force of friction to be 8,339 newtons, which is clearly bigger than the 4,500 newton requirement. So since we have the frictional force is bigger or equal to the centripetal force, we can make the turn. So that's the analysis that you have for example number 3. That was a little harder than most of the centripetal force problems, but we need to be working at this level in order to really analyze through the numbers on real world problems here like this one. So to end this little presentation, I want to show you a couple of animations of a circular motion. As you can see, as this mechanic is having fun and this giant tire as it's moving around, he has to really hold on and pressure himself towards the center to hold on, and using centripetal force towards the center and circling himself around in a circle. Right here, you can see this animation here. This guy did not have enough traction, not enough friction to make it around the circle, and he kept going forward, because centripetal motion says you will just keep going forward if you can't provide enough force to go towards the center. So it's sort of relevant to our lesson here. I hope you enjoyed that. Another one, we have just enough centripetal force to slide onto this curve here. As you can see, the centripetal force is also provided by the acceleration of the car forward, which is quite interesting here in this sort of like Tokyo Drift type of video here. Okay, I hope you enjoyed that, and that's the end of the lesson. Make sure you review and go through the problems again, and I'll see you next time.